A major part of the electrophilic aromatic substitution reaction will be the electrophiles themselves. So what we talked about was that bromine in a typical alkene addition adds easily, but it won't to a aromatic ring because the aromatic ring is so much more stable and less reactive. The bromine itself is just not that good of a nucleophile. But if we throw in a Lewis acid, so our iron bromide is a Lewis acid. Lewis acid means that it has an empty spot where we can add electrons to it. So maybe we think of it as there is a p orbital there that's empty. And so what we can do is the bromine can be a Lewis base, right? It has electrons, so it can add to that empty p orbital. And what we end up forming is a Lewis acid base complex. So we'll have the bromine, and then that pink arrow indicates that we form a bond with the iron. So I'll put that on here. And then we still have the other bromines. So this is our acid-base complex now. And there's going to be a formal charge on that bromine because it has 2 bonds to it, right? And only 2 lone pairs. So it gets a formal positive charge. And the iron now has an extra bond to it. So basically it has now more electrons than it had before, right? Because of the bond. And so there's our Lewis acid-base pair. So this is a stronger electrophile, but what part of it, right? We said it's going to be out here on the end. Because if we think about it, this is a pretty substantial pull on electrons. So the way that we'd used bromine before is we said, oh, at any one time there's a partial negative end and a partial positive end because of the way the electrons can move around and sort of flow. And so we would say that our pi bond could add to that partially positive end, and we'd get the addition that happens with a double bond. Well, that can't happen with this one. It's just not strong enough of a pull. But once we hook it up to the iron, we now have a substantial partial positive charge on that end. And that's what our pi bonds now can attack from the benzene ring. All right? So there's our Lewis acid base complex. Okay, let's look at another Lewis acid, the acylium ion. So I'm giving the example of an acetic anhydride. So again, we have a Lewis acid, and we have some electrons here on our oxygens. So the way this one can work is we could have actually electrons come down here, and that will push electrons here, which will push electrons out to add to the aluminum. So there had to be some sort of close association for this to break apart like that. But what that ends up giving us is the CH3C double bond, triple bond O, sorry, and a plus charge out on the oxygen, plus O double bond CO AlCl3. So again, our Lewis acid base complex. Okay, so it's this part that is the electrophile because it has a resonance form like this, where we can move the electrons back out onto the oxygen, and that will give us the plus charge onto the carbon, and then the lone pairs on the oxygen. So this now is an excellent electrophile for our for our electrophilic aromatic substitution. So this gives us two ways that we can add to this carbon or to this bromine. Those are 2 types of electrophiles.